What specific problem does Autellix aim to solve in the context of LLM serving and agentic programs?
Autellix aims to solve the problem of suboptimal end-to-end performance in LLM serving systems, particularly addressing call-level and program-level head-of-line, whole, blocking that arises from existing scheduling policies like first-come first-served, FCFS, and multi-level feedback queue, MLFQ. These traditional systems fail to consider the dependencies and execution context of LLM calls within agentic programs, leading to significant waiting times and inefficient resource utilization. By introducing a program-aware scheduler that prioritizes LLM calls based on their cumulative execution times and a data locality-aware load balancer, Autellix effectively reduces waiting times and improves throughput. This approach allows shorter programs to complete without being delayed by longer ones, thereby enhancing overall program latency and fairness in resource allocation. Ultimately, Autellix's design focuses on optimizing the execution of dynamic, non-deterministic DAGs of LLM calls, which are characteristic of agentic programs.
How does the proposed Autellix method work? Illustrate step by step, including its architecture and scheduling algorithms.
Autellix operates as a higher-level serving engine specifically designed for agentic programs, focusing on improving end-to-end latency, maximizing GPU utilization, and mitigating program starvation. Its architecture includes a stateful front-end that establishes sessions for programs, a global process table to track program metrics, and a scheduler that prioritizes LLM calls based on program-level statistics. The scheduling algorithms, PLOS, Program-Level Attained Service, and Atlas, Adaptive Thread-Level Attained Service, dynamically assign priorities to LLM calls based on their cumulative execution times, with PLOS focusing on single-threaded programs and Atlas on multi-threaded programs represented as dynamic directed acyclic graphs, DAGs. This prioritization helps reduce both call-level and program-level head-of-line blocking, allowing shorter programs to complete faster. Additionally, Autellix employs a data locality-aware load balancer that routes LLM calls to appropriate engines based on their program's data locality, optimizing performance by minimizing KV cache recomputation.
Can you explain the programming model of Autellix by providing a simplified example that showcases its functionality with specific LLM calls?
Autellix operates on a programming model that treats agentic programs as dynamic, non-deterministic directed acyclic graphs, DAGs, of LLM calls and interrupts. For example, consider a simple agentic program that involves a chatbot interaction where the user first asks, "What is the weather today?" LLM call 1, followed by a follow-up question, "Can you give me a summary of the forecast?" LLM call 2. In this scenario, Autellix would prioritize these LLM calls based on their cumulative execution times, ensuring that shorter calls are executed first to minimize waiting times. If LLM call 1 takes longer to process, Autellix can preempt it to allow LLM call 2 to execute sooner, thus reducing head-of-line whole blocking. Additionally, Autellix leverages a global process table to track the state of these calls, allowing it to dynamically adjust priorities and manage resources effectively across multiple engines, ensuring that the program runs efficiently without unnecessary delays. This model exemplifies how Autellix enhances throughput and reduces latencies by focusing on program-level optimizations rather than individual LLM requests.
What are the theoretical or practical benefits of using Autellix over existing LLM serving systems like VLLM and MLFQ?
Autellix offers significant theoretical and practical benefits over existing LLM serving systems like VLLM and MLFQ by focusing on program-level optimizations rather than individual LLM calls. It effectively reduces both call-level and program-level head-of-line, whole blocking by prioritizing LLM calls based on their program's cumulative execution time, which allows shorter programs to complete faster and minimizes overall waiting times. In practical terms, Autellix achieves up to 15x higher throughput compared to VLLM and 5x higher than MLFQ across diverse workloads, demonstrating its superior efficiency in handling complex agentic programs. Additionally, Autellix's data locality-aware load balancer optimally routes LLM calls to appropriate engines, further enhancing performance by reducing KV cache recomputation. Overall, Autellix's design leads to improved end-to-end latencies and better resource utilization, making it a robust solution for large-scale LLM deployments.
How does Autellix validate its performance? Discuss the metrics and experimental setups used in the evaluation of its effectiveness.
Autellix validates its performance through a series of experiments that evaluate its effectiveness against state-of-the-art LLM serving systems across various representative agentic workloads, including ShareGPT, BFCL, and LATS. The evaluation metrics focus on program-level token latency, defined as the total program response time divided by the number of tokens generated, which provides a comprehensive measure of end-to-end latency for agentic programs. Additionally, Autellix's performance is compared to three baselines: VLLM, VLLM-opt, and MLFQ, with results demonstrating significant throughput improvements, up to 15x higher than VLLM and 5x higher than MLFQ under mixed workloads. The experimental setup involves testing on multiple models: LLM A3, 1-8B, 70B, and Falcon 180B, across different GPU configurations, ensuring a robust assessment of Autellix's capabilities. Furthermore, the evaluation includes metrics for tail latency, 95th and 99th percentiles, showcasing Autellix's ability to maintain lower latencies compared to its competitors, thus confirming its effectiveness in real-world scenarios.
What limitations or potential drawbacks does the Autellix approach have, particularly in terms of scalability or complexity in dynamic environments?
The Autellix approach, while innovative, has limitations regarding scalability and complexity in dynamic environments. Firstly, Autellix is non-clairvoyant, meaning it operates without prior knowledge of program workloads or execution graphs, which can hinder its ability to optimize scheduling effectively in highly variable scenarios. This lack of foresight may lead to suboptimal performance when faced with unpredictable workloads, as the system dynamically constructs its internal representation of the execution graph during runtime. Additionally, the reliance on a global process table to track program metrics introduces overhead, which could become a bottleneck as the number of concurrent programs increases, potentially affecting responsiveness. Furthermore, while Autellix's load balancing strategy improves throughput, it may still struggle with maintaining optimal performance under extreme load conditions, particularly if many long-running programs compete for resources, leading to potential starvation of shorter programs. Lastly, the complexity of managing multiple engines and ensuring data locality can complicate deployment and maintenance, especially in environments with diverse workloads.